All right, guys, so Unit 8 starts with a review of summations and just sigma notation to sum together a whole bunch of terms. And it takes place in Appendix E of the textbook. So we're going to be looking at that part of the textbook just for a couple days, and then we'll be doing some integral stuff using the concepts from this appendix. So just a brief review of summations. We do use sigma, this Greek letter sigma, to indicate that we're adding together a whole bunch of terms. So in this case, we've got what we call the index, right? So that tells us where to begin. It's telling us to start at m, and m could be any integer, right? So it's saying plug in to our function some integer, and then we will have the m term of that integer, right? And then we'll have one more than m. So if m is 2, then we're going to plug in a 2. If m is, and then after that, it's going to be plugging in a 3, which would be one more than 2. And then we would plug in a 4, which is 2 more than 2. So whatever m is, I'm going to add one more than that and plug that in. 2 more than m, plug that into my function. 3 more, 4 more, all the way up until I'm 1 less than this number, which is an integer. And then finally, I'll plug in this number, which is another integer. So essentially, we're going to take all the integers. And remember, I has to take on only integers. Between m and n. So we'll do some examples with some actual numbers here, but this is not supposed to be a new thing. Okay, so we've got a few examples here, and we're going to write this sum in expanded form. So in this first case, our function is I squared, and it's saying that our index says to start at 1. So the first thing I'm going to do is plug in a 1, right? I'm going to have 1 squared. And then I'm going to plug in the next integer after that, which would be 2, and I have to add those together. And I have to do the same thing for plugging in a 3 and plugging in a 4. And I'm stopping at 4 because that's where it says to stop plugging in integers. All right, so I add all these together. I got 1 plus 4 plus 9 plus 16, which should be 30. And there is a way to do this in Desmos, but right now we're going to start learning some rules that are going to help us do these algebraically. Okay, the next example, I is simply just the linear function I, all by itself. So I'm going to plug in a 3 first, and then I'm going to plug in a 4, and then I'm going to plug in a 5, and I'm going to keep doing this until the last things that I plug in are n minus 1, right? 1 less than n, and n. And there's nothing I can do to actually evaluate this because n is not an integer, but this is a representation of what is described here. Plugging in a 3, then a 4, then a 5, all the way up to n. And that would be the end of it, because right now I can't actually evaluate that. A similar case here, we're asked to evaluate the function 1 over k, beginning with when k equals 1. And remember, this is a good example of the index variable not having to be I all the time. Sometimes it may be x or n or k or something else. So the first thing that we're plugging in here is a 1. And then I'm going to plug in the next integer after 1. Right? And then the next integer after that. And I'm not plugging in decimals, it's only integers. That's what these summations do. They only use consecutive integers between your index and wherever it's stated to stop plugging in. And this will go all the way until we're at 1 less than k, and finally we're at k, right? So that's me plugging in those variables for each of these. Similar to the last example, we can't actually get those values. I'm sorry, I shouldn't have used k there. I should have used n. Because n is the thing that we're plugging in at the very end, right? N is where we are stopping. So I'm plugging in an n for k at the end. Finally, we've got a function here that looks rational. We've got an I minus 1 in the numerator and an I squared plus 3 in the denominator. It's kind of a mess. And I'm asked to start by plugging in a 1. So this is going to be 1 minus 1 over 1 squared plus 3. So that's the first term, right? I've plugged in a 1 everywhere that I had an I. And then next, I'm going to plug in the integer that comes after 1. And I'd encourage you to do these on your own. right? Because these are not super challenging. You should be able to figure out the concept behind this. And I'm just replacing I with the next integer each time. This we could actually evaluate. This first term here is 1 minus 1, which is 0 divided by 4. So the first term is 0. The second term is 1 over 7, so we've got 1/7. And the final term is 2/12. In order to add these, I should get a common denominator, and I think a good one here would be 42. And so I'll end up with 13 over 42 when I combine all these. So just some practice using summations and seeing them in action, and knowing that it's not always going to end with an integer, right? We may not always get an actual result that is numerical. It might just be an expression. So we've got a theorem here that has a number of components to it, and we're going to use these components to help us moving forward with some further examples. And there are a number of elements to some different theorems that are in this section of the textbook. So what I'm going to do is combine some of the theorems from within Appendix E into just this one page that we can see them all. There are actually going to be more than just these 5, so I'll call the next ones after that F, G, and H, because there are a number here that we're going to use. So the first theorem, I'm just going to write it out and then I'll explain it. Okay, so if I have some function f of I and it's being multiplied by c, and I plug in an m, and then an m plus 1, and then an m plus 2, all the way up to n, and it's a sum of that function times c, I can remove that constant from the summation and rewrite this as the constant times the summation from m to n of f of I. This is a trick that we're going to want to use pretty frequently here. So just like with limits and some other concepts where we've seen this, you can remove those constants, and that's going to be a trick that's going to be useful to us moving forward. If I am taking the sum, again, from m to n, where n and m are integers and m is less than n, of a function minus another function, I'm going to write beneath it that you could calculate that sum for the first function and then calculate it for the second function and subtract those. Right? So this works with addition and it also works with subtraction. We'll have our other one here be the same thing, just with addition. So that's another trick that we'll want to use. If we can separate these components, just like we would with limits, you'll see that these laws have a lot of parallels with our limit laws. A simple one here is that if I am taking the sum of my elements from when I equals 1 all the way up to n, and the function is just a constant function, 1, the last number I'm plugging in here is n. This is going to equal n. There is nothing for me to plug in to this function. So all I'm doing with this constant number 1 is adding it together n times, right? And the key is that this is a 1. I plug in a 1, I get a 1. I plug in a 2, I get a 1. Plug in a 3, I get a 1. And how many times am I adding these 1s together? N times. So I end up with n. That's a theorem that is going to be useful if we can get these summations to the point where we are summing 1 n number of times. And then we've got a few that start to get a little bit more complicated. If instead of that being a 1, it is a function, but a simple function. So from when I equals 1 to n of c, right? So this is some constant, not necessarily a 1. Then that sum is going to be whatever c times n is. So similar to the last example, but times whatever that value is. All right, a few more here. And I'm going to write them out and then state what their value is. So these next 3, we could spend some time proving them. If we get back to school, we might do that. But I'm going to give you a formula that can replace each of these sums. So if I am taking the sum from when I is 1 through n, and this is the variable here. The whole function is just this linear function I. That means I'm plugging in a 1, then plugging in a 2, then a 3, then a 4, stopping at n, and adding all of those together. There's a simple formula that you might remember from when we dealt with arithmetic sequences last year that is just n times n plus 1 over 2. And so this is a formula we can use to replace this summation, something algebraic that we can actually calculate here. If it's an I squared instead, then it's n times n plus 1 times 2n plus 1 over 6. And again, these are formulas we're going to want to apply at different times. So this theorems page is a pretty useful page. I would make sure that you've got these somewhere in your notes, easy to access. And then if it's an I cubed function, then the way that I'm going to evaluate this is n times n plus 1 all over 2 and that whole expression squared. And you'll find these in the textbook as well. But we are going to use combinations of each of these different theorems with some complicated sums throughout the first chapter of this unit here. So one example that I want to do together, we're going to use some of those theorems to help us here when we evaluate this sum that we've got in front of us. And the first thing I'm going to do when I evaluate this sum is I am going to bring this I inside here because we don't have any way to deal with a product of two things when I'm adding these functions together. None of our rules dealt with products. So I'm going to rewrite this as the sum from when I equals 1 to n of 4i cubed minus 3i. And that's my first step here. Now what I'm going to do here is apply the second, or rather the third theorem that we wrote down on the last page and separate these so that I can rewrite this instead as the sum from 1 to n of 4i cubed minus the sum from 1 to n of 3i. I'm separating them because I have some tools that'll help me evaluate each of these individually. Another thing that I'm going to do with this first sum is take this constant out because that was something we discussed that we can do. So finally I'm going to rewrite this as 4 times the sum from 1 to n of I cubed. And I'm going to do the same thing with the 3 here, minus 3 times the sum from 1 to n of I. And this is where I can apply the second to last or third to last and last theorems that we wrote down in our notes. So this is going to be 4 times, and we said that the sum from when I equals 1 to n of I cubed is the same as n times n plus 1, and in this case n is still just a variable, we don't have a value for it, divided by 2 squared. So we're just applying those theorems. Minus 3 times, and we saw that if the function is just simply the linear function x or I, whatever the index variable is, I can replace this with n times n plus 1 over 2. And so now I can just do a little bit of work to try to simplify this expression. So there are some things that I could do to help here. I'm going to rewrite this first term as 4 times. And if I square this whole expression, then I'm going to have n times n plus 1, and I'm going to leave that squared, just so that we can see this differently, over, and 2 squared is 4, so you'll see that those 4's cancel, minus 3n times n plus 1 over 2, and all I've done is just move that 3 to the numerator. So what I'm going to do here is factor out an n times n plus 1, because I have that in each of these terms. So sometimes factoring helps us simplify here. So we've got an n times n plus 1, factoring that out. I'm going to use square brackets here. And then I've got an n times an n plus 1 minus 3 halves. All right, so I'm going to work to combine these fractions over here. We're going to need a common denominator of 2. So this is n times n plus 1 over n times n plus 1 minus 3 over 2, and this is going to be a 2n times n plus 1 if I want those to be able to be combined like that. And so I'm just going to distribute what I've got here, and then I can combine these two expressions because I'll actually be able to multiply them. So I've got n times n plus 1 times 2n squared plus 2n minus 3 over 2. All right, and I could multiply these two things together now, and I have one expression, n times n plus 1, and I don't need the square brackets anymore, 2n squared plus 2n minus 3 all over 2. And this is an expression that I can use now that represents the value of that original statement. So this is, and I can keep going here, this. And it's an expression I can use to represent that. So we'll see some more complicated ways to apply those theorems, but you should be referencing those theorems and applying them every chance you get to try to simplify some of these expressions, because tonight I'm just going to give you the bookwork, and that'll be due Wednesday at midnight. But tomorrow we'll see some more examples from Appendix E and how these theorems can be applied.